Hello everybody, and thank you for this opportunity and thank you for the introduction. Convion, yes, as explained, is a systems company. We develop these mini power plants based on solid oxide fuel cell technology. And by these systems, this product is a solution for ultra clean and efficient power generation in small scale. It's a local solution which can realize many purposes in different market segments. Which way? A bit of background. I will discuss today the product, the applications, the aspects relating to today's topic of energy security, as well as our ongoing demonstration and its possibilities. The team of Convion all came from Wärtsilä Fuel Cell Group that has, for the entire duration of its existence, focused on systems development. We don't develop the fuel cells or cell stacks. We've always devoted all of our attention on the system integration, the process technologies, automation, power electronics, as well as applications. Wärtsilä discontinued the activity in 2012. We established a new company and started operating independently in 2013. We are a fairly technology-heavy or technology-intensive small company with a lot of IPR in the relevant technologies, and focus on this mid-range SOFC. In the range of power generation, these are small systems, but for a fuel cell system, tens and hundreds of kilowatts is a fairly large unit size. It doesn't matter that, it doesn't mean that the technology wouldn't be applicable to different sizes. This is a range that we believe there is a lot of potential. The value that a local solution can provide can be maximized in this medium range, and the auxiliary costs related to the installation are relatively lower than it would be in a very small scale. There should be first customer delivery in Q3, unfortunately. The first unit was delivered in the summer, but it spent the summer in Italy. I wish I could have. And we expect to start up the system very soon this month in Italy. So the product brief summary, it's this compact integrated power module which can operate alone or in a parallel configuration of several modules. Currently, the electrical efficiency is above 53. It's quite a lot dependent on the stacks, and today we saw some very respectable figures for the stack efficiency. We foresee this to be above 60 very soon. And it's a CHP capable system, so the total efficiency can be above 80. We also realize the potential of fuel flexibility in this module. SOFC by nature is fuel flexible. It's capable of internally reforming hydrocarbons. But we have quite a lot of background on designing the systems for actually varying qualities of fuels. And then this is important in small size, particularly where there's not necessarily, for example, with biogas, a necessarily means to upgrade the gas to the kind of standard pipeline quality. Also, this is compatible with the current and the future energy systems. We can use natural gas as it is. We can use natural gas with some hydrogen blended in. We can use diluted gases with CO2 kind of ballast together with methane. And as one of the value propositions of fuel cells is the security on site, the security for the local installation. the system is capable of forming an island and securing the loads nearby or on site. Today we've heard of many of the concepts that I will be talking about, so that makes my job easier. But so that this wouldn't only be about future, there's a little bit of history as well. The team has actually developed self-contained integrated power units of different generations over the years, and with an aim of coming up with solutions that are robust enough, scalable enough, and future-proof enough for large numbers of deployed units in the field. Initially, we started with 20 kilowatt systems, natural gas as well as biogas systems. What's called new energy there, that's actually a landfill gas system, special case, very diluted fuel, but a great learning experience for us for developing the automation and controls of the system, because the fuel quality would vary very dramatically. There was also kind of two sister units fueled by methanol for marine use. This is a marine auxiliary unit. A couple of 50 kilowatt laboratory units for biogas and natural gas during the Wärtsilä years. And then Convion took all of the IPR, took all of the good ideas and integrated them together, simplified everything to the bare minimum without compromises in performance and maximizing the flexibility. And we came up with the startup's first product, the C50. We are a small company. We work on the technology and on this product, but we also keep our eyes open on what's happening in the operating environment. And I think the turmoil currently in the energy sector is rather creating opportunities than kind of leaving us out or closing us out. There is an ongoing electrification, share of electricity, and value of electricity, and emphasis on the quality of electricity and security of supply is ever more important. A pressing need to reduce CO2 emissions and other environmental impact of power generation is high on every agenda. And then there are new needs, for example, the ability to compensate for the intermittency of the other renewables. And then accelerating these changes are new technologies, digitalization, storage, deregulation, making possible two-way participation into the power grids, and which was also mentioned in the previous presentation, the active end user, the prosumer. Energy security is not a new need. But it's probably the urgency or importance of it has heightened recently. I must confess that the illustration was inspired by the image in the former presentation. Energy security could be defined or explained in many ways, but you could at least see these dimensions. The time dimension from reliability to availability, from the millisecond level frequency compensation through the capacity markets or service restoration through grid planning and so forth. So it could be from milliseconds to decades to make sure that there is energy available for whomever needs it. And then there's the other dimension of costs and benefits, internal, external, and it's an important part of the energy security that it's actually accessible, it's affordable, and then that the negative impacts of energy generation aren't too massive or they are on a sustainable level. And I think fuel cells can contribute to all of these. We can provide support for the grid in terms of capacity. We can reduce the dependence on finite resources or imported resources. We can improve the fuel economy and we can reduce the emissions. We've been talking about future. We've grown used to the idea of centralized generation. Over the decades, the advantages of central generation were always so high. Central generation and central control were so high that they justified the disadvantages related to distance, such as vulnerability and losses. Gradually, we hear more about decentralized or even distributed network structure of the grid, which may sound futuristic, but Navigant Research, they just said that next year, 2018, the new additions in the distributed generation will surpass new additions of central generation. So it's actually massive things are happening, and we have to acknowledge that fuel cells are not even making a big splash here. This is about solar, it's about wind, and unfortunately it's also a lot about diesel gensets or conventional technologies. But since it's probably not realistic to imagine that one technology would change everything, it's a hybrid solution. We have to find a path from this point to the future point. This trend supports the adoption of fuel cells. Why fuel cells? Fuel cell, it's kind of inherently modular. Small units have the equal performance to very massive units. You have a lot of repeated parallel units, the cells, cell stacks, and assemblies and systems. And then it makes it particularly suited for distributed generation. There is no reason in terms of fuel economy to have a massive and optimized system. You can have a small system close by and get rid of the transmission distribution losses and the vulnerabilities. And this is basically it, that we can beat the central generation already now with the first unit produced, and then we can also only see improvement in the future. And this is a conservative estimate. Usually the central generation doesn't perform that well. Potential applications for us, the buildings, the industrial installations, they could be agricultural or municipal installations, where heat can be used, or some of the kind of additional benefits of fuel cells, not that only energy, not that only power, but also heat or redundancy when we operate next to the grid, or the possibility of utilizing a local fuel. Usually these are the early market anyway, through which we can then conquer the bigger market potential. There is a mention of the Demosoft project, which is an FCH JU project, a very interesting one, and I wish I could show you the live view now, but some approvals and automation issues need to be solved, and the unit will start in a couple of weeks. We also see that you can foresee a different world, but you have to find a path to that world, and the grid can be renewed a microgrid at a time. These are like small miniature versions of the grid, and many of the advantages of individual technologies, when combined, they kind of multiply. And a fuel cell system close to the loads, close to the thermal loads, and possibly controllable storage or other generation, together they can form an optimized solution. Again, maybe we can go further. storage is a big issue. A lot of talk about batteries, but with an on-site grid parallel generation unit, you can often either get rid of the battery altogether or a backup generator, or you can at least reduce the size of it and all of the costs associated to that, because the battery doesn't generate anything. It provides a service, but it doesn't generate anything. With a fuel cell which is capable of islanding, forming an intentional island and securing the local loads, we can often manage without the battery. Often you hear that SOFC is for base load. It's for continuous operation, but it doesn't have to be for base load. It modulates efficiently, quite quickly as well. And if you imagine a fleet of these systems and you match their production to the thermal loads, for example, then you can maximize the total efficiency of the primary energy use completely, and electricity is what you transmit between the installation. Here's also an illustration of how our system is configured. We can, with some limitations, we can form an island where our system is the only generator without the storage, and we can form a load following capability on a millisecond level with some loss in efficiency for the duration of the outage. It's usually in European societies, for example, most of the outages are very short in duration, but it's actually the number of outages that causes the loss to, for example, businesses or society, often not so much the duration. And we can ride through the problem of some seconds or minutes easily and form a load following capability. We can imagine prosumerism, buildings becoming kind of active participants to the grid. We foresee that the hybrid solutions of different technologies will be the future, rather than individual technologies solving all of the problems. This is about the DemoSoft. So this is the site, an aerial view of a medium-sized wastewater treatment plant in Turin area in north of Italy. It's not the only plant in Turin, but it's there. We didn't have to build it for the project, so it was a good one. And they had biogas production available already, but wasn't used in a very valuable way, so they only generated heat out of it for the plant to operate. And now we can bring fuel cell modules to the site. We have designed the integration to the plant so that the SOFC module's waste heat covers 100% of the thermal loads of the process, the preheating of the wastewater sludge, and then approximately 30% of the electrical loads of the plant. The system installation could be increased with several modules if necessary. We have tried to match the capacity with the amount of gas available throughout the year. What's a particular beauty of this application is that there are thousands and thousands of wastewater treatment plants in the world, and they are more or less the same in terms of technology. When you bring in a person from another plant to this place, that they will recognize everything, and so it's a very replicable application. Only scale varies. And when you consider, there are the Sankey diagrams of SOFC as compared to a typical piston engine genset of this scale, the efficiency would be something 30-something, electrical efficiency at the sweet spot. They would have plenty of heat, but there's no need for that much of heat in the process. Usually in small biogas installation, the margins, profit margins are not so large. There's a feasibility limit, and it doesn't make sense to run an engine. You would really have to find a way of standardizing and mass producing the technology to make it kind of feasible. But fuel cell can open up new market, and that's where usually wastewater and other bio wastes are just treated just because the waste needs to be treated, but they don't recover the thermal, the energy content of it, or do that only partially. And this is an interesting application, because if you look at the very large wastewater treatment plants, usually they are beautifully optimized already. They have efficient piston engines with extra turbines and many things. So the efficiency of conversion is very good, but when you go to those thousands of other plants where there's nothing, or they only treat the waste but they don't recover the energy, this is where we have a lot of future market potential. And these are in the order of entering load. The unit is population equivalent. We have omitted the 10 biggest sites because they are so big that the others would be almost like negligibly small. So these are the next almost 1,000 sites. And here in the mid-range, that's where majority of the number of the plants are. And this is the range for 1 or 2 or some fuel cell modules of our size, and where usually they don't have any power generation. I said I wanted to show you a running system. This is what we did before shipping the system. We ran a reduced scale, the same system but with a reduced batch of stacks, just to validate the solutions and the fuel flexibility. There's a 5,000 hour stint. We had some teething issues in the beginning with some automation, but once this was corrected, the system performed quite well, or better than expected actually. We got a good efficiency and good continuous operation. We carried out the island mode tests as well, and the efficiency here is a little bit lower because it's a reduced scale. There are some fixed losses in the system that are relatively, their share is relatively higher of the 20 kilowatt. Once we have the full 60 kilowatt of stacks, then the efficiency is somewhat higher, which can be seen here. We have 54.7 net efficiency in the system. This is a laboratory result with a mix of 6% methane and CO2 blended in, just to simulate the biogas operation. This is from March this year, and the unit is now in Italy. We are finalizing the little things. Oh, it's always the little things that are left last, and we'll start up the system later this month. The message that I want to say is that energy system is always a mix of technologies, mix of fuels, and transition from one to another kind of state requires a design path. SIFC is a technology with all of the flexibilities that can operate as a transition technology, but it's also future-proof. because, for example, with synthetic natural gas or biogas, we can provide carbon-neutral electricity with no local emissions at a very high efficiency in the future. And in the previous presentation, we saw the different ways of approaching the biomass as a primary initial feedstock. If you think of how the conversion takes place in the fuel cell, we don't mix air and fuel, we only let oxygen to react. And fuel cell actually probably provides a better means for capturing carbon because you don't mix it with a lot of nitrogen. And bioenergy could have this special property of providing negative CO2 emissions. Yes, I'll be happy to show you around at Convion in Italy if you happen to be over there. And we wish to develop further installations like this. Thank you.